Vertices are a phenomenon relating to great circles. By definition, a great circle has the same centre and radius as the Earth itself. The vertices of a great circle are the northernmost and southernmost position of the great circle. The vertices are antipodal, in other words, diametrically opposite. From the example on the screen, the northern vertex of the great circle is 63 degrees north and 10 degrees east. The southern vertex will have the same value of latitude, except it is south, in this case 63 degrees south. The great circle will have these two antipodal points on a meridian and its antimeridian. In this example, the northern vertex is on the 10 east longitude meridian, and the southern vertex is on the 170 degrees west longitude antimeridian. The sum of the two longitudes will always equal 180 degrees, indicating a meridian and its associated antimeridian. Vertices have some interesting properties. The great circle will cross the equator at the 2 points whose longitude is 90 degrees from either vertex, in this case 100 east and 80 west. The great circle will cross the equator at an angle equal to the latitude of its vertex. In this case, the angle is 63 degrees. The direction of the great circle can be determined from this crossing angle. At either vertex of the great circle, the track direction is either 090 or 270 degrees. All meridians converge to a point at either pole. Depending on the proximity of a track to the pole and the relative angle, track direction can change quite rapidly. Sometimes it is useful for ease of navigation to follow a track that does not change direction. Constant changes in track nowadays do not pose a significant problem, as technical advances in navigation equipment can easily cope with constant track changes. A line that does have constant direction is called a Rhumb line, and this line will cut each meridian at the same angle. A Rhumb line therefore has the advantage of a constant track. From the diagram on the screen, we can see that a typical great circle track follows a different path over the Earth's surface to the Rhumb line track, between the same departure and destination positions. The disadvantage of flying a Rhumb line track is that it is not normally the shortest distance between 2 points. However, there are some special cases of Rhumb lines that do create the shortest distance, in addition to being of constant direction. For example, the equator. The track along the equator is either west or east. It is a Rhumb line as the track is constant, but it is also the shortest distance between 2 points, as it is a great circle. Another is a meridian. A meridian is both a semi-great circle and a Rhumb line. The track along a meridian is either north or south. The equator and all meridians display qualities of both great circles and Rhumb lines. They follow the shortest path along the Earth's surface, and they are also of constant direction. The Rhumb line is always nearer to the equator than its corresponding great circle path. The shape of the Rhumb line can be described as convex to the equator. Conversely, it can be described as concave to the nearer pole. In the picture on the screen, you can see that the Rhumb line direction is constant between A and B, whereas the great circle track is increasing from approximately 060 degrees to around 100 degrees. The Rhumb line track is approximately 070. In this next example, we can see the Rhumb line track from Moscow to Vancouver. It can be seen that the path of the run line almost follows a line of latitude, in a constant westerly direction. The Great Circle track, on the other hand, has a northerly track, a lot closer to the North Pole. The different paths that the Rhumb line and Great Circle follow can be seen even more drastically when portrayed on particular maps, as can be seen on the screen. Comparison of the Rhumb line and Great Circle tracks on a global scale are depicted on the screen. You can see that in the Northern Hemisphere, tracking easterly, that the Great Circle track starts at 030 degrees and finishes at 150 degrees. In other words, the Great Circle track is increasing. When flying in an easterly direction in the Southern Hemisphere, it can be seen that the Great Circle track is decreasing from 150 degrees to 030 degrees. When flying westerly, the opposite occurs. The Great Circle track is decreasing in the Northern Hemisphere and increasing in the Southern Hemisphere. An easy way to remember what happens to the Great Circle track in relation to the Rhumb line track is the mnemonic DIID. The image shows 4 segments, the North and South Hemispheres, and a westerly and easterly track. For example, in the Northern Hemisphere on a westerly track, the Great Circle path is D for decreasing, and in the Southern Hemisphere in a westerly direction, the Great Circle track is I for increasing. This is a useful aid memoir and is used to solve many navigational questions. To summarize, we have seen that a great circle is a circle on the surface of the Earth whose centre and radius are the same as that of the Earth. It also prescribes the shortest distance between 2 points. Vertices are the most northern and southern positions of a great circle track. Small circles are circles on the surface of the Earth that do not have the same centre or radius as that of the Earth. A Rhumb line is a line of constant direction. It is also important to recall the aid memoir DIID to solve some navigational problems.